Welcome to Cosmic Sedation, a place where stars sing you softly to sleep. Tonight, we journey through Titan's mysterious methane lakes, exploring their tranquil depths under the calmness of deep space. Don't forget to subscribe and like if you're enjoying this cosmic bedtime story. Where are you listening from tonight? And what time do you usually drift off? Let's hear it in the comments below. As the stars align, let's begin our peaceful night journey together. Titan's methane lakes paradoxically evaporate into a nitrogen-rich sky, fueling unpredictable weather systems that challenge terrestrial understanding. The coldest place in our solar system where liquids exist is not deep space, but on this distant moon orbiting Saturn. At minus 179 degrees Celsius, the surface of Titan is cold enough for methane to remain liquid, yet it continuously evaporates into the atmosphere. Methane molecules at Calmness surface dance upward through a process driven by cosmic rays that penetrate up to 3 meters below. These high-energy particles alter the chemical composition beneath the lake's surface, creating complex hydrocarbons like propane. This evaporation is akin to water evaporating from Earth's oceans, but at a temperature where we would expect methane ice to form. The evaporation rate of Calmness, spanning an area larger than the Great Lakes combined, is crucial for the moon's weather patterns. Winds on Titan blow at speeds comparable to a gentle breeze on Earth, measured by Cassini at about 1 meter per second. These breezes create ripples in Lakebeds, waves just 2 centimeters high, barely noticeable but significant enough to indicate atmospheric activity. The wind-driven evaporation from Titan's lakes is far slower than what we experience on Earth due to the moon's thin atmosphere and extreme cold. Yet this process is relentless, continuously feeding methane into an atmosphere that is 98% nitrogen with traces of other hydrocarbons like ethane. This composition creates a dynamic interplay between surface and sky, unique in our solar system. Cosmic rays vary their diffusion rates across Titan by factors of 10 due to the moon's magnetic field strength and atmospheric density fluctuations. These variations influence the chemical processes beneath each lake differently. In some areas, the rate of hydrocarbon formation is higher than others, leading to localized changes in weather patterns. This phenomenon mirrors the diverse climates on Earth shaped by ocean currents and mountain ranges. On Titan, cosmic rays are the invisible sculptors of its atmospheric chemistry, a process that has been ongoing for billions of years since Titan formed with Saturn. The continuous evaporation from Titan's lakes not only affects local weather, but also contributes to global climate cycles. The methane released into the atmosphere condenses into clouds and eventually returns as ethane rain or snow. This cycle is slower than Earth's water cycle, taking centuries instead of days or months. Each molecule that evaporates from the lake's surface embarks on a journey that can span hundreds of years before returning to its liquid state. For perspective, this means that a single drop of methane could take as long as it took for human civilization to develop and spread across Earth. Calmness, Titan's largest lake, holds secrets beneath its waves. At an average depth largely unknown, but estimated to be around 100 meters in some areas, the lake's bottom remains shrouded in mystery. The pressure at these depths is significantly lower than on Earth due to Titan's weaker gravitational pull and thinner atmosphere. Yet, this environment supports a unique ecosystem of simple organic molecules that could hint at prebiotic chemistry. While we have yet to detect life on Titan, its lakes are dynamic systems where the interplay between cosmic rays, evaporation rates, and atmospheric composition creates an ever-changing landscape. As we continue to explore this distant moon, each discovery deepens our understanding of how worlds far from Earth can sustain their own intricate cycles of life and weather. In the dead of night on Earth, temperatures can plummet to -230 degrees Celsius in Antarctica. But this is a balmy climate compared to Titan's surface, where it averages -179 degrees Celsius. This frigid environment allows methane lakes to exist as liquid, not ice or vapor, and they play host to an unexpected cosmic ballet. Cosmic rays, high-energy particles from deep space, are penetrating up to 3 meters into these lakes, transforming the simple mixtures of methane and ethane below. While we often associate such high-energy phenomena with distant stars and supernovae, these processes are quietly occurring beneath a moon far from our own planet. Each cosmic ray that strikes Titan's atmosphere generates showers of secondary particles, which descend into the lake's depth. These interactions can break apart molecules or fuse them together, creating a variety of organic compounds. The process is slow but relentless, and it operates on an entirely different timescale than Earth's chemistry. Here, a molecule might take thousands of years to react, whereas similar reactions would occur in mere seconds under sunlight on our home planet. This stark contrast highlights the unique conditions of Titan, where chemical reactions proceed at a pace that seems almost suspended in time. The largest lake, Krakenmeer, covers an area larger than any of Earth's Great Lakes. It is so vast that if you were to stand by its shore, it would stretch beyond your sightline. Yet, beneath its surface, the depth averages around 100 meters in some areas, with unknown depths elsewhere. As cosmic rays diffuse through this liquid methane, they introduce a degree of complexity into Titan's chemistry that scientists are only beginning to understand. The energy from these particles can cause methane molecules to combine with nitrogen and other elements present in the atmosphere, potentially leading to the formation of more complex organic compounds like amino acids or even simple proteins. On Earth, such processes could be crucial for life's origins. On Titan, they may be shaping a chemical landscape that remains entirely alien. Titan's magnetic field, while weaker than Saturn's, still varies in strength across its surface. This variation influences the rate of cosmic ray diffusion, creating areas where these high-energy particles penetrate more deeply into the lakes and others where their effects are diminished. The result is a patchwork of chemical activity beneath the methane seas, with some regions richer in complex molecules than others. Imagine this on Earth. Certain lakes being more biologically active simply because they receive more cosmic radiation. In Titan's case, these variations could influence the distribution of organic compounds and perhaps even provide clues about potential prebiotic chemistry. Despite the extreme cold and lack of sunlight, the waves detected on Ligeia Mare in 2014 offer a glimpse into how wind patterns interact with Titan's surface liquids. These waves are gentle, only 2 centimeters high, but they suggest wind speeds of around 1 meter per second. This movement stirs the lake's surfaces, allowing for the exchange of gases between the liquid and atmosphere. As cosmic rays continue their work beneath the liquid, this interaction could introduce even more complexity into Titan's chemical mixtures. The combination of wave motion and deep diffusion creates a dynamic environment where organic compounds are constantly being created and altered. The processes occurring in Titan's methane lakes have been unfolding for billions of years, dating back to when Saturn itself formed around 4.5 billion years ago. Over this vast timescale, the interactions between cosmic rays and Titan's atmosphere have likely played a significant role in shaping its chemical landscape. This environment offers scientists a unique laboratory to study prebiotic chemistry under conditions vastly different from those on Earth. While it remains unlikely that life as we know it could exist in these frigid lakes, the potential for simpler forms of organic molecules means Titan continues to be an intriguing subject for exploration and scientific inquiry. The surface of Kraken Mare is a canvas etched by time beyond human comprehension. The lakes on Titan are sculpted not just by wind and rain, but by cosmic rays penetrating their depths, processes that unfold over geological epochs far longer than any civilization has persisted on Earth. These rays, invisible to the eye yet powerful in their influence, diffuse through up to 3 meters of liquid methane. They break apart molecules into fragments and rearrange them into new compounds. The process is slow. A single ray might take 1 billion years to alter one molecule, but when scaled across the vast expanse of Titan's lakes, it transforms the landscape over millennia. Imagine if every grain of sand on Earth shifted position once in 1,000 lifetimes. This is what cosmic diffusion does for these liquid methane seas. While we marvel at the waves that ripple across Ligeia Mare, reaching mere centimeters in height, the true shaping force lies beneath the surface. The temperature here averages -179 degrees Celsius, cold enough to freeze nitrogen, yet warm enough for complex organic molecules to form and rearrange. This dance of particles, driven by cosmic rays, is a microscopic ballet that subtly carves out the basin over billions of years. If you could stand on the edge of one of these lakes, you might feel a cool breeze brushing against your skin, but no sound would reach your ears. Sound waves need molecules to travel, and here they simply wouldn't exist. Remarkably, the very same cosmic rays that sculpt Titan's lakebeds also contribute to the formation of complex organic compounds. While these compounds are limited in size due to the cold environment, their presence hints at a chemistry far richer than expected for such a distant world. The diffusion process is not uniform. It varies by a factor of 10, depending on local magnetic field strength and atmospheric density. This variability means that some areas experience faster molecular rearrangement, while others change more slowly, shaping the landscape in unique patterns over time. As we consider the age of these lakes, billions of years old, we realize they predate even the earliest forms of life on Earth by eons. The lakes have existed long enough for Saturn itself to have formed and cooled from a swirling cloud of gas and dust. Yet, their evolution is so gradual that it would take an observer millions of lifetimes just to notice significant changes. The methane lakes are not merely passive bodies of liquid, but dynamic systems where the boundary between the liquid and the universe above is constantly shifting. On Earth, erosion by water or wind might reshape a landscape in a matter of centuries. Here on Titan, however, the forces at work are both more patient and less predictable. The waves that disturb Ligeia Mare's surface move at speeds comparable to a gentle breeze on Earth, but they are dwarfed by the slow, invisible churn beneath the liquid. This dance between cosmic radiation and hydrocarbon chemistry will continue for eons, crafting shapes in the lakebeds that may never be fully understood until we can visit and observe them directly. In the distant reaches of our solar system, Titan orbits Saturn, hosting vast lakes of methane and ethane on its frigid surface. Mare, the largest lake, spans an area larger than any of Earth's Great Lakes, covering approximately 400,000 square kilometers. This expansive body of liquid could easily accommodate several continents side by side, yet it remains largely unexplored. The silence here is profound, a result of the thin atmosphere and low-pressure conditions on Titan. There are no ripples or splashes to disturb the surface, creating a quiet that defies expectations for an environment with liquids. On Earth, we associate water bodies with sound. Waves lapping at shores, fish darting beneath the surface, or raindrops falling into puddles. But on Titan, these familiar sounds do not exist because there are no molecules to carry sound waves through its near-vacuum atmosphere. Despite this stillness, occasional methane mist can form along the lake edges, creating a faint fog that occasionally rolls over the surface, adding an unexpected layer of activity. Below Mare's tranquil liquid surface, cosmic rays penetrate up to 3 meters deep, altering the chemical composition of the methane and ethane mixture. These reactions occur at temperatures so cold that methane remains liquid, while water would be frozen solid on Earth. The process unfolds over geological timescales, far beyond human comprehension. This continuous interaction between cosmic rays and lake chemistry is akin to a slow dance, where each step taken by these high-energy particles shapes the molecular landscape. Wind speeds of about 1 meter per second create gentle waves no taller than 2 centimeters across some parts of Ligeia Mare, another of Titan's lakes. This minimal activity contrasts sharply with the bustling life and weather we imagine around our planet's bodies of water. Surprisingly, these slight disturbances are not caused by wind alone, but also by the slow seepage of methane from underground reservoirs, a process that subtly reshapes the lakebed over time. The chemical composition of these lakes is shaped by cosmic rays, which vary in intensity across different regions due to variations in magnetic field strength and atmospheric density. In some areas, cosmic ray diffusion rates can be 10 times higher than others, leading to significant differences in the formation of complex organic compounds beneath the surface. This variability introduces a layer of complexity not found on Earth, where uniformity is more common. The depth of Kraken Mare remains largely unknown, with estimates ranging from an average depth that is yet to be precisely determined to over 100 meters in some areas. This uncertainty adds a layer of mystery to Titan's lakes, much like the uncharted territories on early Earth maps. Yet beneath this enigmatic surface lies a world shaped by cosmic processes over geological epochs far longer than any civilization has persisted on Earth. Scientists have used sonar mapping techniques to estimate that Kraken Mare could be as deep as 150 meters in certain spots, with an average depth of around 80 meters. Cosmic rays not only influence the chemical composition beneath the surface, but also affect the atmosphere above, contributing to the formation of hydrocarbons like propane and ethane. These compounds play a role in shaping the Moon's atmospheric chemistry, creating a feedback loop where surface processes are intertwined with those high above. This interconnectedness highlights the complexity of Titan's environment, a system where every element contributes to the larger picture. The organic molecules formed through cosmic ray interactions could potentially lead to prebiotic chemical reactions, hinting at possibilities for life beyond Earth as we know it. However, these conditions are far from conducive to complex life forms due to the extreme cold and lack of readily available energy sources. Yet, the potential for basic chemical building blocks to form under such unique circumstances adds a layer of intrigue to Titan's lakes. Scientists speculate that certain amino acids or nucleobases might be synthesized in these environments, providing a foundation for more complex organic structures. Titan's atmosphere, composed primarily of nitrogen and methane, plays a crucial role in the Moon's weather systems. Unlike Earth, where water vapor is dominant, Titan's weather is driven by hydrocarbons like ethane and propane. This difference introduces an entirely new set of atmospheric phenomena, from cloud formation to precipitation patterns that are alien yet intriguing. The surface of Kraken Mare has been shaped not just by wind and rain, but also by the slow erosion caused by cosmic rays penetrating its depth. Over billions of years, these particles have subtly altered the landscape, creating unique geological features that reflect the Moon's long history. This process is a stark reminder of how cosmic forces can shape worlds in ways that are both subtle and profound. Cosmic rays not only influence the chemical composition beneath the surface, but also affect the atmosphere above, contributing to the formation of hydrocarbons like propane and ethane. Cosmic rays bombard Titan's surface, interacting with methane molecules in its lakes to create new chemical pathways. At Kraken Mare, these interactions occur up to 3 meters beneath the liquid surface, where temperatures hover around -179 degrees Celsius. This frigid environment allows for unique reactions that would be impossible on Earth. The cold slows molecular motion, making it easier for cosmic rays to induce changes in methane and ethane molecules. These processes are not uniform across Titan. In some regions, the magnetic field is stronger, reducing the penetration of cosmic rays into the lakes. This variability leads to distinct chemical environments within Crock and Mare, each with its own unique characteristics influenced by the ambient energy from distant stars. The depth of these interactions can vary significantly, affecting the complexity and diversity of compounds formed. Understanding how cosmic rays influence Titan's chemistry is crucial for unraveling the Moon's history. The lakes on Titan are estimated to be billions of years old, dating back to the formation of Saturn's moon itself. This ancient environment provides a glimpse into chemical processes that could have been common in the early solar system. On Earth, similar reactions occur, but at much faster rates due to higher temperatures and more abundant energy sources. The waves detected on Ligeia Mare by Cassini spacecraft provide indirect evidence of wind patterns influencing the lake's surfaces. These gentle ripples are a result of winds blowing across the surface at speeds of about 1 meter per second, creating waves as high as 2 centimeters. This interaction between atmosphere and liquid is a rare occurrence in our solar system, where most celestial bodies lack both stable liquids and atmospheres. Interestingly, the organic compounds formed through cosmic ray interactions on Titan are limited by the available energy at such low temperatures. Larger molecules require more energy to form, which is scarce in this cold environment. This constraint shapes the chemical diversity of Titan's lakes, creating a unique ecosystem where only certain types of complex structures can exist. The depth of Crock and Mare remains largely unknown due to technical challenges posed by its remote location and the lack of effective solar power at such distances from Saturn. However, even in this darkness, cosmic rays continue to weave intricate patterns, crafting molecules that could potentially support life forms adapted to such extreme conditions. Each molecule involved in these reactions follows its own path, influenced by the ambient energy from distant stars. At the molecular level, cosmic rays initiate a cascade of events as they collide with methane molecules. These high-energy particles can break apart methane into hydrocarbons and other compounds, setting off a chain reaction that leads to the formation of more complex organic structures. This process is akin to a microscopic factory, where each collision represents a step in the production line. The resulting chemical diversity within Titan's lakes could offer clues about the potential for life elsewhere in the universe. The interaction between cosmic rays and methane molecules on Titan mirrors processes that occur in Earth's upper atmosphere, but at vastly different scales. On our planet, similar reactions happen much faster due to higher temperatures and more abundant energy sources. However, these interactions on Titan provide a slower motion view of how complex organic compounds might form under cooler conditions. This comparative study helps scientists understand the fundamental principles governing chemical evolution across varying environments in space. As cosmic rays penetrate deeper into Crock and Mare, they encounter an increasingly dense mixture of methane and ethane. The density of this liquid medium affects the rate at which these reactions occur, creating a gradient of molecular complexity from the surface to greater depths. This depth-dependent chemistry offers insights into how environmental factors influence chemical processes in extraterrestrial environments. Each layer within the lake holds its own unique story of interaction between cosmic rays and the local environment. The ancient lakes on Titan have been subjected to this ongoing process for billions of years, allowing ample time for complex organic molecules to accumulate. This long timescale contrasts sharply with the rapid changes we observe on Earth, where life evolves and adapts in a matter of millions or even thousands of years. The slow pace of chemical evolution on Titan underscores how different time scales can shape planetary environments in profound ways. Within these cold, liquid lakes, the formation of complex organic compounds is not just a product of cosmic ray interactions, but also influenced by the Moon's unique atmospheric composition. Nitrogen dominates Titan's atmosphere, providing an environment rich in nitrogen. In deep space, cosmic particles traverse an average distance of about 10 light-years before encountering Titan's atmosphere. These high-energy rays, originating from distant supernovae and black holes, journey through the cosmos until they reach Titan's nitrogen-rich sky. Here, their diffusion rate varies based on atmospheric density and magnetic field strength. The cosmic particles can penetrate up to 3 meters into Kraken Mare, a depth equivalent to several city buses stacked vertically. This penetration affects the chemical composition of the methane-ethane mixture beneath the surface. Each particle carries enough energy to break apart molecules, initiating complex reactions that unfold over millennia in this frigid environment. On Earth, such interactions occur under extreme pressures at oceanic depths. Yet here, it is the cold temperatures that stabilize these processes. The cosmic particles can reach depths of up to 10 meters within Kraken Mare, where they interact with layers of methane-ethane mixtures that have never been directly observed. This deeper penetration leads to unique chemical reactions not seen in shallower regions, potentially creating more complex organic compounds. These interactions could be crucial for understanding the Moon's potential for harboring prebiotic conditions. Titan's atmosphere acts as a selective filter for cosmic rays, allowing fewer particles into its lakes than might otherwise be expected due to its density and composition. Within Kraken Mare, the particles interact with molecules over distances that would span several city blocks on Earth. These interactions can lead to the formation of increasingly complex organic compounds, setting in motion chemical processes unique to this distant moon. Unexpectedly, despite Titan's dense atmosphere, cosmic rays manage to penetrate deeper into its lakes than they do into Earth's oceans due to the lower gravitational pull and higher molecular density. This phenomenon creates spatial variations in chemical activity across Titan's surface, with more complex molecules forming near the lake edges where the atmosphere is thinner. The waves detected by Cassini on Ligeia may provide insight into how these cosmic interactions influence surface dynamics. At only 2 centimeters high, these ripples are gentle compared to Earth's oceans, but significant given Titan's thin atmosphere and cold temperatures. Wind speeds of around 1 meter per second generate these waves, slow enough to allow for steady diffusion beneath the liquid's surface. This equilibrium is crucial for the chemical processes that occur over long periods, contributing to Titan's unique chemistry. The depth of Kraken Mare remains largely unknown beyond estimates, suggesting parts may reach 100 meters. This uncertainty adds an intriguing element to our understanding of cosmic particle penetration. As particles diffuse into deeper regions, they might interact with layers of methane-ethane mixtures that have never been directly observed. These unexplored depths hold secrets about the Moon's history and potential for chemical evolution. The temperature at Titan's surface averages around -179 degrees Celsius, making it cold enough for methane to exist as a liquid rather than vapor or ice. This environment is so extreme that it challenges our understanding of chemistry and physics as we know them on Earth. The coldest place in the known universe is not deep space, but in laboratories on Earth. Yet here, on Titan's surface, temperatures are just right for these unique chemical processes to occur. Cosmic ray diffusion also impacts the age of organic compounds within Kraken Mare. While the lake itself may be billions of years old, the molecules formed through this process are constantly being remade and transformed. This ongoing cycle of creation and transformation ensures that even though the environment is ancient, it remains dynamic and ever-changing. The iron in your blood was forged in stars that died before our sun existed. Similarly, these cosmic particles have been traveling for eons to reach Titan's surface, carrying with them the story of distant stellar explosions. The waves on Ligeia may not only indicate wind speeds, but also suggest the presence of tides. These subtle movements are driven by Saturn's gravitational pull and could influence the rate at which cosmic rays diffuse into the lakes. The interplay between these forces creates a delicate balance that allows for consistent interaction between particles and molecules beneath the surface. This equilibrium is crucial for the chemical processes that occur over long periods, contributing to Titan's unique chemistry. As we reflect on the age of Kraken Mare, it becomes clear that this moon has been undergoing cosmic particle penetration for billions of years. The cumulative effect of these interactions has shaped not only the lake's composition, but also its potential for harboring prebiotic conditions. While the environment is inhospitable to life, as we know it, the chemical processes unfolding here offer a glimpse into the possibilities of life elsewhere in the universe. Kraken Mare, Titan's largest lake, spans an area larger than any of Earth's Great Lakes, covering approximately 400,000 square kilometers. Beneath its icy surface, geothermal activity generates warmth that defies the planet's frigid -179 degrees Celsius average temperature. This heat is enough to maintain liquid methane and ethane up to 3 meters beneath the ice crust in some areas of Kraken Mare. The paradox here lies in how a moon so cold can sustain such warm conditions deep within its lakes. Cosmic rays, originating from distant supernovae and black holes, penetrate Kraken Mare's surface, interacting with the liquid methane and ethane below. These high-energy particles can affect chemical processes up to 3 meters beneath the lake's icy exterior. The varying magnetic field strength and atmospheric density on Titan influence how deeply these cosmic rays can penetrate, creating a complex interplay of reactions within the lakes. This variability introduces an element of complexity in understanding how organic compounds are formed under different conditions across Titan's surface. The warmth beneath Kraken Mare's ice crusts is crucial for maintaining liquid methane and ethane at temperatures above -183 degrees Celsius, which is the boiling point of methane at 1 atmosphere. Geothermal activity raises the temperature to this critical threshold, ensuring that these hydrocarbons remain in a liquid state rather than freezing into solids or evaporating away. This delicate balance has persisted for billions of years, offering a unique window into the chemical processes that could have occurred during early Earth's history. Kraken Mare's estimated average depth remains largely unknown, but some areas are speculated to be as deep as 100 meters. In these deeper regions, the warmth not only maintains liquid methane and ethane, but also fosters complex chemical reactions necessary for potential organic compound formation. The presence of such warm zones in a lake that spans over 400,000 square kilometers is remarkable given Titan's overall frigid environment. Cosmic ray diffusion rates vary by a factor of 10 across different parts of Titan due to its varying magnetic field strength and atmospheric density. However, the depth at which these particles can penetrate also depends on local ice thickness. In some regions, cosmic rays can reach up to 5 meters beneath Kraken Mare's surface, affecting a wider range of chemical reactions compared to shallower areas where penetration is limited to just 2 meters. This variability introduces an element of complexity in understanding how organic compounds are formed on Titan's lakes. While sound cannot propagate through the vacuum of space, the effects of cosmic ray bombardment can be felt in the chemical composition of Kraken Mare's liquid mixture. This interaction is crucial for understanding not only Titan, but also other celestial bodies where similar processes might occur. The warmth beneath the ice crusts serves as a reminder that even in the coldest reaches of our solar system, there are hidden sources of energy and potential for life to evolve under unexpected conditions. The depth of Kraken Mare is estimated at around 100 meters in some areas, with an average depth largely unknown. This variability in depth influences the extent of cosmic ray penetration and the resulting chemical reactions beneath the surface. The deeper regions provide a more stable environment for complex molecules to form, protected from the harsher conditions closer to the ice crust. The liquid methane and ethane within Kraken Mare are not static. They undergo continuous interactions with cosmic rays and other environmental factors. These processes could potentially lead to the formation of larger organic compounds over time, though the cold temperatures limit the complexity of these molecules. The chemical activity beneath the ice crusts is a dynamic process that unfolds over geological timescales, offering insights into planetary evolution and the potential for life. Buoyancy in Titan's methane seas would feel distinctly different from any terrestrial experience. Your body, composed largely of water, would float effortlessly on the surface of Kraken Mare. a lake larger than any of Earth's Great Lakes at approximately 400,000 square kilometers. The liquid methane is so cold, averaging minus 179 degrees Celsius, that it remains in its liquid state without freezing or evaporating. This environment offers an unusual form of buoyancy, where the density of the liquid methane supports your body weight more effectively than water on Earth due to its lower density. In this alien sea, you would float with ease, feeling lighter than you ever have before because Titan's gravity is only 14% that of Earth's. The sensation of floating in liquid methane contrasts sharply with familiar experiences on Earth. Imagine the buoyancy as a gentle embrace from an environment where the laws of physics are subtly different. The lack of pressure, waves means sound, cannot travel through the liquid, creating an eerily silent world. This silence is not due to distance or vastness, but rather the absence of molecules capable of carrying sound vibrations. In this setting, communication would rely on other methods, perhaps visual signals or direct contact. Descending beneath the surface reveals a different kind of depth. The methane lakes are estimated to be hundreds of meters deep in some areas, with an average depth that remains largely unknown due to the challenges of exploration. As you dive deeper, cosmic rays penetrate up to 3 meters into the liquid, influencing its chemical composition and potentially creating complex organic compounds. These high-energy particles from distant stars and supernovae interact with methane molecules, forming structures that could exist nowhere else in our solar system. The surface tension of Titan's lakes is another fascinating aspect. Unlike water, which forms droplets on a smooth surface, liquid methane spreads out more easily due to its lower surface tension. This property would allow you to glide effortlessly over the liquid surface if you were to swim or float. The texture of the liquid against your skin would be cool and slick, offering a sensation unlike any other earthly experience. Your movements through this environment would feel fluid and graceful, as if you are floating in an invisible medium. The chemical interactions within Titan's lakes create an intriguing laboratory far removed from Earth's conditions. Methane and ethane mix to form a liquid that is rich in hydrocarbons. These compounds can only exist in their complex forms due to the extremely low temperatures on Titan, which prevent larger molecules from breaking down or reforming too quickly. This stability allows for unique chemical pathways that could lead to the formation of organic structures not found elsewhere in our solar system. The potential for these reactions to occur over billions of years is a reminder of how time and environment can shape chemistry. Kraken-Mare's vastness stretches your perception of space and scale. At 400,000 square kilometers, this lake dwarfs even the largest earthly bodies of water. Its size is not just impressive in terms of area, but also in its historical context. These lakes have existed for billions of years, dating back to Titan's formation alongside Saturn itself. The enduring nature of these liquid bodies challenges our understanding of what constitutes a stable environment on an extraterrestrial world. As you float on Kraken-Mare, it's humbling to reflect on the vastness and age of this alien sea. untouched by human hands, yet full of scientific potential. The vastness of Saturn's rings is a spectacle that dwarfs even Titan itself. Covering an area over 140 times larger than Earth's surface, these rings are composed of countless icy particles orbiting at various distances from the planet. Each particle traces its own unique path in response to Saturn's gravitational field. Yet amidst this grandeur lies Titan, a moon so small it seems almost insignificant when compared to the majesty of Saturn's rings. If we were to scale down these celestial bodies to fit within an average urban park, the rings would stretch across several city blocks, while Titan might be no larger than a pebble nestled between them. The contrast is stark, yet both are intricately linked by their shared orbit around Saturn. Imagine standing on the shores of Mare, the largest lake on Titan, which spans an area greater than Lake Superior. At -179 degrees Celsius, your breath would instantly condense into methane fog, and any exposed skin would quickly freeze. Waves as high as 2 centimeters ripple across the surface, driven by winds barely strong enough to lift a feather on Earth. Despite this apparent tranquility, cosmic rays bombard these lakes from all directions, penetrating up to 3 meters beneath their surfaces. These high-energy particles travel an average distance of 10 light-years through interstellar space before encountering Titan's atmosphere, bringing with them a story of distant stars and supernovae. In the scale of our solar system, these lakes are mere dots on an otherwise empty canvas, dominated by Saturn's expansive rings. The process of cosmic ray diffusion within Titan's methane seas is not uniform. It varies by factors of 10 across different regions due to fluctuations in atmospheric density and magnetic field strength. This phenomenon creates a dynamic environment where chemical reactions proceed at different rates, shaping the complex hydrocarbon mixtures beneath each lake's surface. The interaction between these cosmic particles and the liquid hydrocarbons can be likened to an unseen symphony playing out silently below the waves. Each region of Mare could have its own unique composition, influenced by local conditions that dictate how deeply and frequently these rays penetrate. This variability underscores Titan's complexity as a world where the universe itself continually interacts with its surface in subtle yet profound ways. Cosmic rays are not just transient visitors to Titan. They have been influencing the moon's chemical evolution for billions of years, long before life emerged on Earth. These high-energy particles carry energy from far-off supernovae, which have exploded millions or even billions of years ago. This connection between Titan's lakes and the broader universe is both humbling and awe-inspiring. As we stand on the shore of Mare, we are not merely observing a distant moon, but also witnessing a relic from the early stages of our galaxy's formation. The chemical reactions initiated by these cosmic rays could be similar to those that occurred in the primordial soup on Earth, offering insights into how life might have originated elsewhere. The temperature at the surface of Mare hovers around -179 degrees Celsius, conditions so cold that liquid methane can exist without freezing. This frigid environment allows for chemical reactions that would be impossible on Earth due to the higher temperatures and pressures here. However, even in such extreme conditions, life has found a way, though not as we know it. Microbial organisms capable of surviving and thriving under these harsh circumstances might exist within Titan's lakes, utilizing the abundant methane and ethane available for their metabolic processes. While scientists have yet to discover definitive evidence of extraterrestrial life on Titan, the possibility remains tantalizing, offering a glimpse into what life could be like in other parts of the universe. Surprisingly, some researchers speculate that these organisms might not rely solely on liquid methane, but also on solid forms of hydrocarbons found at the bottom of Mare, creating an entirely different form of biochemistry. Mare, Titan's largest lake, spans an area larger than any of Earth's Great Lakes, covering approximately 400,000 square kilometers. Beneath its surface, geothermal activity generates warmth that defies the planet's frigid -179 degrees Celsius average temperature. This internal heat source could be crucial for the formation and maintenance of complex organic molecules in Titan's lakes. The depth of Mare is estimated at around 100 meters in some areas, with an average depth that remains largely unknown. In contrast to the vastness of Saturn's rings, which stretch over hundreds of thousands of kilometers, the relatively small size of Titan and its lakes becomes even more pronounced when considering their potential role in supporting lifelike processes in such a cold environment. Cosmic rays, originating from distant stars and supernovae, traverse the void of space for millions of years before encountering Titan's dense atmosphere. These high-energy particles interact with methane molecules in Mare, diffusing up to 3 meters beneath its surface. Each cosmic ray carries energy far exceeding that found on Earth, yet within Titan's frigid environment, their impact is softened by the cold. The temperature at the surface of Mare hovers around -179 degrees Celsius, where liquid methane exists rather than freezing into ice or evaporating away. This extreme cold means that even as cosmic rays break down methane molecules, they do so in a manner unique to this distant moon. The diffusion process varies across different regions of Titan due to its varying magnetic field strength and atmospheric density. In equatorial zones, where the atmosphere is thinner, particles can penetrate deeper, up to 3 meters beneath the surface, compared to polar regions. This variability underscores how environmental factors shape the interaction between cosmic rays and methane on Titan. Cosmic ray diffusion contributes not only to chemical reactions, but also subtly influences the lake's surface dynamics. The Cassini spacecraft detected waves measuring about 2 centimeters high in Mare, indicating wind speeds of around 1 meter per second. These gentle breezes, though modest by Earth standards, are enough to create ripples on Titan's lakes and interact with cosmic ray-induced chemical changes. The journey of these particles from distant stars is an extraordinary feat of nature. They travel for millions of years across the vastness of space before reaching Titan's atmosphere. Some cosmic rays originate from supernovae that exploded long before our sun formed, carrying energy from ancient stellar explosions to shape Titan's current environment. Mare, the largest lake on Titan, spans an area larger than any of Earth's Great Lakes at approximately 400,000 square kilometers. Its depth remains a mystery, with estimates suggesting it could be around 100 meters in some areas, but largely unknown elsewhere. This uncertainty adds another layer to the study of cosmic ray diffusion and its effects on Titan's methane seas. Cosmic rays also influence the atmospheric composition above Mare, where nitrogen and methane predominate. As they break down methane molecules, they release hydrogen and other hydrocarbons into the air. This interplay between cosmic radiation and Titan's atmosphere contributes to its unique chemical makeup, enriching the environment with a variety of compounds that could have implications for future exploration. The process by which cosmic rays interact with methane is not just chemically complex. It also involves an intricate dance of energy transfer over billions of years. Each collision within Mare represents a moment in time where ancient stellar events meet the cold surface of Saturn's moon. This interaction between distant stars and Titan's lakes underscores the interconnectedness of our universe. Despite the cold temperatures on Titan, organic compounds can form complex structures up to a certain size due to cosmic ray interactions. However, larger molecules require more energy than is available in this frigid environment. The boundary for molecular complexity here serves as a reminder of how environmental conditions shape possibilities across the cosmos. These chemical processes hint at potential pathways for life's building blocks under different planetary conditions. Cosmic rays can penetrate up to 3 meters into Titan's lakes, affecting the chemical composition of the methane and ethane mixture below the surface. This penetration depth varies by a factor of 10 over different parts of Titan due to its varying magnetic field strength and atmospheric density. The interaction between cosmic particles and the liquid environment creates a dynamic process that is both intricate and unpredictable. The organic compounds formed through these interactions are subject to further transformations as they rise into Titan's atmosphere, where they can be broken down or recombined by solar radiation. This cycle of creation and destruction highlights the continuous exchange between the surface and the sky on this distant moon, offering insights into how such processes might occur elsewhere in the universe. Cosmic rays penetrate up to 3 meters into Titan's methane lakes, altering their chemical composition and contributing to a complex interplay of processes that extend beyond the immediate vicinity of these vast bodies of liquid. These high-energy particles, originating from distant stars and supernovae, interact with molecules in Mare, breaking down larger hydrocarbons and releasing hydrogen atoms that form new compounds like acetylene and ethylene. This process occurs not just at the surface, but also deep within the lake, where temperatures hover around -179 degrees Celsius. The depth of these interactions varies across Titan's lakes due to differences in magnetic field strength and atmospheric density, leading to a patchwork of chemical diversity. Mare, Titan's largest lake, spans an area larger than any of Earth's Great Lakes at approximately 400,000 square kilometers. This expansive body of methane plays a crucial role in Titan's climate dynamics by influencing weather patterns up to 1,500 kilometers away from its shores. The temperature difference between the surface of Kraken Mare and the colder atmosphere drives convection currents that can reach altitudes of over 10 kilometers, affecting wind speeds and cloud formation across vast distances on the Moon's surface. These interactions are part of an intricate system where local processes have widespread effects, shaping Titan's climate in ways that defy terrestrial understanding. The varying intensity of cosmic ray diffusion rates across different parts of Titan creates unique chemical signatures within its lakes. In regions with weaker magnetic fields, these particles can penetrate deeper into the liquid, leading to more extensive breakdowns of larger molecules and the formation of new compounds. This uneven distribution means that some areas experience tenfold differences in the extent of molecular alteration compared to others. For instance, near the equator where cosmic ray diffusion is most intense, the lakes contain higher concentrations of acetylene and ethylene, while at higher latitudes with weaker fields, methane remains relatively unaltered. These variations contribute to a complex chemical landscape within Titan's lakes, each with its own unique composition influenced by cosmic ray activity. The temperature at the surface of Kraken Mare averages around -179 degrees Celsius, cold enough for methane to exist in liquid form rather than ice or vapor. This frigid environment allows the lake waters to play host to an unexpected cosmic ballet, where high-energy particles from distant stars and supernovae interact with molecules deep within the lakes. These interactions not only alter chemical compositions, but also influence the physical properties of the liquids, such as density and viscosity. The extreme cold ensures that these processes unfold over geological timescales, contributing to the long-term stability of Titan's climate system. Interestingly, the colder temperatures near the lake's bottom can slow down diffusion rates, creating a stratification effect where deeper layers remain relatively unchanged compared to shallower ones. The depth of Kraken Mare remains largely unknown, with some areas estimated at around 100 meters deep. However, even this vastness pales in comparison to the scale of Titan's methane cycle. The entire Moon acts as a giant hydrocarbon reservoir where evaporation and precipitation occur over timescales beyond human lifespans, shaping weather patterns across its surface. A single drop of methane might take centuries to complete its journey from lake to atmosphere, illustrating the slow but profound impact of these processes on Titan's climate dynamics. The temperature at the surface of Kraken Mare averages around -179 degrees Celsius, cold enough for methane to exist in liquid form rather than ice or vapor. This frigid environment allows the lake waters to play host to an unexpected cosmic ballet, where high-energy particles from distant stars and supernovae interact with molecules deep within the lakes. These interactions not only alter chemical compositions, but also influence the physical properties of the liquids, such as density and viscosity. The extreme cold ensures that these processes unfold over geological timescales, contributing to the long-term stability of Titan's climate system. Cosmic rays penetrate up to 3 meters into Titan's methane lakes, where they interact with molecules in a process that unfolds over geological epochs far longer than any civilization has persisted on Earth. These high-energy particles break down larger hydrocarbons into smaller ones, releasing hydrogen atoms that form new compounds like acetylene and ethylene. This chemical transformation occurs at temperatures of -179 degrees Celsius, where methane remains liquid despite the frigid environment. The depth variations within Crach and Mare create different conditions for these reactions, with deeper regions offering more stable environments for prolonged interactions. In some areas of Crach and Mare, the lake reaches depth exceeding 100 meters, while in others it remains relatively shallow. These varying depths influence how cosmic rays affect the liquid's chemical composition. Deeper waters provide a more consistent environment for complex reactions to occur, whereas shallower regions experience greater turbulence due to wind and wave action. This variability contributes to the unique character of Titan's hydrological cycle, shaping its landscape over billions of years through subtle yet persistent erosion patterns. The flow rates within Crach and Mare are influenced by factors such as wind speed, atmospheric density, and magnetic field strength. These variables create a complex interplay that shapes the Moon's surface over time. For instance, regions with higher wind speeds experience more turbulent flows, leading to increased wave action and shoreline erosion. Conversely, areas with steadier currents in deeper waters allow for prolonged chemical reactions, potentially fostering the formation of more complex molecules. This variability highlights how diverse environmental conditions can drive unique geological processes on Titan. In some unexpected cases, however, these steady currents can also lead to the accumulation of organic compounds along specific shorelines, creating localized zones rich in potential prebiotic chemistry. The surface temperature of Crach and Mare averages around -179 degrees Celsius, cold enough to maintain methane as a liquid rather than ice or vapor. At this temperature, organic compounds can only form up to a certain size due to the limited energy available in such a frigid environment. Despite these constraints, the chemical reactions occurring within the lake offer insights into how prebiotic chemistry might have unfolded on early Earth under similar conditions. Objects floating on Crach and Mare experience a specific buoyancy of 0.82 grams per cubic centimeter, significantly less than water's 1 gram per cubic centimeter, creating an entirely different sensory experience for any observer. Over billions of years, the flow rates and erosion patterns in Titan's methane lakes will continue to shape its landscape. These processes are slow and steady compared to terrestrial equivalents, but have profound implications for understanding cold environments where liquid exists as methane rather than water, ice, or vapor. As cosmic rays interact with the lake's contents, they contribute to ongoing chemical transformations, further influencing the Moon's hydrological cycle. This long-term evolution underscores how Titan's lakes play a crucial role in shaping its surface over eons. The depth of Kraken Mare remains largely unknown, with estimates suggesting that some areas reach depth exceeding 100 meters. These variations influence both the flow rates and chemical reactions within the lake. Deeper regions provide more stable environments for complex reactions to occur, while shallower waters experience greater turbulence due to wind and wave action. This dynamic interplay between depth, temperature, and cosmic ray penetration highlights how Titan's lakes are not just passive reservoirs, but active participants in the Moon's long-term evolution through their unique hydrological processes. Cosmic rays pierce through Titan's thick atmosphere, interacting with methane clouds in a subatomic dance that defies immediate observation. These high-energy particles traverse the dense nitrogen layers and dissolve into liquid hydrocarbons beneath Kraken Mare's surface, up to 3 meters deep. Each collision within these clouds shatters larger molecules into fragments, setting off chains of reactions that reshape Titan's chemical landscape. The temperature at Kraken Mare averages around -179 degrees Celsius, a condition so cold it challenges our terrestrial understanding of liquids and gases. Yet, cosmic rays manage to penetrate far beyond what one might expect in such an environment. This penetration is not just a function of the particle's energy, but also the unique composition of Titan's atmosphere, which allows for deeper diffusion than on Earth despite its frigid temperatures. These particles travel through the liquid methane with remarkable efficiency, breaking down larger hydrocarbons into smaller compounds like acetylene and ethylene. The subatomic reactions within Titan's atmosphere are influenced by localized variations in magnetic field strength and atmospheric density. In regions with weaker magnetic fields, these particles have greater freedom to move and interact, leading to more extensive chemical changes. This variability can be mapped across the lake's surface, revealing patterns that hint at the dynamic nature of Titan's chemistry. Scientists use data from Cassini to chart these interactions, providing a detailed map of how cosmic rays influence different parts of Kraken Mare. Notably, the diffusion rates vary by a factor of 10 over different areas due to these variations, showcasing the complexity of this process. Each interaction on Titan's surface is linked to stellar phenomena far beyond our solar system, bridging the gap between local chemistry and galactic events. These particles originate in supernovae explosions and traverse the galaxy for millions or billions of years before reaching Titan. The sheer distance these particles travel underscores how interconnected all parts of the universe truly are. This journey means that each interaction on Titan's surface is a remnant of distant cosmic events, contributing to the unique chemical composition of Kraken Mare. Understanding these processes provides insights into potential prebiotic conditions on early Earth. The cold temperatures and hydrocarbon-rich environment of Kraken Mare mimic those of our planet before it developed an oxygen-rich atmosphere. By studying Titan, researchers can explore analogous environments that may have led to the formation of organic compounds necessary for life. This knowledge helps bridge the gap between astrophysics and astrobiology, offering clues about how complex molecules formed under similar conditions. Specifically, the breakdown of larger hydrocarbons into smaller ones releases hydrogen atoms that form new compounds like acetylene and ethylene. The chemical transformations within Kraken-Mare are not static, but evolve over time due to continuous cosmic ray bombardment. These changes occur at a pace far slower than what we experience on Earth, unfolding over geological epochs that span billions of years. This slow progression means that the lake's chemistry reflects not just current conditions, but also the history of Titan's environment, offering a window into its ancient past. Each layer of liquid methane holds clues about the moon's evolution and the role cosmic rays have played in shaping its chemical composition. Over time, these interactions create a complex mixture of compounds that could serve as building blocks for more intricate molecules. Kraken-Mare is estimated to be billions of years old, dating back to the formation of Saturn's moon itself. The depth of Kraken-Mare varies, with some areas reaching around 100 meters, while its average depth remains largely unknown due to the challenges of exploring such a distant and cold environment. Despite these limitations, scientists continue to gather data that reveals more about this vast lake's composition and history. The continuous interaction between cosmic rays and methane molecules in Kraken-Mare highlights how processes on Titan can inform our understanding of chemical evolution in extreme environments elsewhere in the universe. On Titan's surface, liquid methane fills vast lakes such as Kraken-Mare, a body of water larger than any of Earth's Great Lakes. Methane here behaves much like water does on our planet, forming seas and rivers that shape the landscape over geological timescales. Yet, beneath these similarities lies a fundamental difference. While Earth's ecosystems rely on liquid water as their foundation, Titan's lakes are primarily composed of methane with traces of ethane. This hydrocarbon mixture supports unique chemical reactions that would be impossible in our warmer world. The cold temperatures on Titan, averaging around -179 degrees Celsius, keep methane stable in a liquid state. In contrast, water on Earth exists as ice at much higher temperatures due to its molecular structure. The stark difference between these two substances is highlighted by the fact that cosmic rays can penetrate up to 3 meters into Titan's lakes, altering their chemical composition through ionization and breaking down larger hydrocarbons. This process releases hydrogen atoms, forming new compounds like acetylene and ethylene. On Earth, such reactions would be far less pronounced due to the higher energy required for similar transformations in water-based environments. Interestingly, some of the organic compounds formed by cosmic rays on Titan could potentially serve as precursors to life. While complex molecules can form here, their size is limited by the cold environment and available energy. This process mirrors early Earth conditions where simple organic molecules were synthesized under different environmental constraints. These reactions hint at a shared chemistry across vastly different worlds, suggesting that basic building blocks of life might emerge in similar circumstances throughout the universe. In Titan's methane seas, waves measure about 2 centimeters high, driven by wind speeds averaging around 1 meter per second. This gentle motion contrasts sharply with the violent storms common on Earth, where ocean waves can reach heights of up to 15 meters or more. The calmness of these alien waters is a product not only of their composition, but also of Titan's distant location from the Sun, which limits solar energy inputs and thus wind generation. Despite this, the lakes are dynamic environments where surface interactions with cosmic rays initiate chemical reactions that could lead to complex organic molecules. The depth of Kraken Mare remains largely unknown, with estimates suggesting it ranges between 30 meters in shallower areas to over 100 meters elsewhere. This variability adds another layer of complexity to Titan's hydrology. On Earth, the deepest point in our oceans, the Mariana Trench, reaches depths far beyond what is recorded on Titan. Yet, both environments host unique ecosystems adapted to their respective extremes, illustrating how life can adapt under different planetary conditions. Cosmic rays penetrate up to 3 meters into Titan's methane lakes, where they interact with molecules and create new compounds. These high-energy particles break down larger hydrocarbons, releasing hydrogen atoms that form acetylene and ethylene. This process is akin to the weathering of rocks on Earth, but operates at a molecular scale. The chemical reactions in these cold environments are slow yet persistent, shaping Titan's lakes over billions of years. Understanding these processes helps us appreciate how similar fundamental chemistry can operate under vastly different conditions across the solar system. At the edge of Kraken Mare, the largest lake on Titan, you stand in a landscape utterly alien to Earth's familiar cues. The surface temperature hovers at -179 degrees Celsius, cold enough for methane to remain liquid rather than vapor or ice. Your breath condenses into visible plumes as you exhale, each molecule of nitrogen and methane in your exhalation joining the atmosphere that envelops this distant moon. This frigid environment is so unlike Earth's that even the simplest actions feel otherworldly. The vastness of Kraken Mare spans an area larger than any of Earth's Great Lakes, covering approximately 400,000 square kilometers. Yet, despite its size, you notice something peculiar. Sound cannot travel here as it does on Earth. The dense atmosphere, composed mainly of nitrogen and methane, lacks the molecular density to carry sound waves. In this silence, your voice would be a private whisper, unheard by any potential observer nearby. The isolation is profound, yet it also heightens awareness of the lake's surface, which ripples gently under faint winds. As you gaze across Kraken Mare, the landscape lacks familiar landmarks such as trees or mountains. Instead, vast expanses of liquid methane stretch toward distant horizons, their surfaces shimmering with a metallic sheen. The waves here are minute, only about 2 centimeters high, but they carry information about wind speeds averaging around 1 meter per second. These gentle ripples are the result of cosmic ray diffusion affecting the lake's surface tension and chemical composition beneath. This process, invisible to the naked eye, subtly shapes the landscape over millennia. The depth of Mare remains largely a mystery, with estimates suggesting some areas reach up to 100 meters below the surface. Cosmic rays penetrate these depths, interacting with methane molecules in complex ways that influence the lake's chemical makeup. These high-energy particles travel from distant stars and supernovae, journeying for millions of years before reaching Titan's atmosphere. Their interaction here is a reminder of the interconnectedness of our solar system, where events light years away can alter the chemistry on this far-flung moon. The surface tension of Mare is unlike any liquid you've encountered on Earth. Methane at -179 degrees Celsius behaves in ways that challenge terrestrial expectations. For instance, it does not freeze into ice because the conditions here prevent water-like crystallization. Instead, methane remains fluid, its molecules locked in a delicate balance between solid and gas states. This unique state of matter is a testament to the extreme cold on Titan, where temperatures are so low they defy everyday experience. As you stand by Mare, the moon's distant sun, Saturn itself, casts an eerie glow over this alien landscape. The light from Saturn is dim compared to Earth's sun, providing less than 1% of the illumination we take for granted. In this muted light, Titan appears as a world suspended in time, a place where geological processes unfold at a pace far slower than on Earth. The methane lakes here are billions of years old, dating back to the formation of Saturn's moon itself. This ancient environment is a living laboratory, offering insights into the early stages of planetary evolution and the potential for life elsewhere in the universe. The boundary where dry land meets Mare on Titan is a dynamic frontier shaped by seasonal methane evaporation and condensation cycles. Unlike Earth's shorelines, which are influenced by tides and waves, Titan's shores expand and contract over decades as its frigid climate dictates the flow of liquid methane. This process has been ongoing for billions of years since Titan's formation alongside Saturn. At this boundary, cosmic rays penetrate up to 3 meters into Mare, breaking down larger hydrocarbons like ethylene and acetylene. These high-energy particles, originating from distant stars and supernovae, interact with methane molecules in a process that unfolds over geological epochs far longer than any civilization has persisted on Earth. This continuous interaction provides insights into how organic chemistry might develop under similar conditions elsewhere in the universe. The surface tension at Mare's edge is influenced by faint winds moving at about 1 meter per second. These gentle breezes create subtle ripples, marking the transition from solid ground to liquid methane. Despite Titan's harsh conditions, these ripples offer a rare glimpse into how weather patterns manifest on this distant moon. The boundary zone becomes a site where atmospheric and surface interactions are delicately balanced. The depth of Mare remains largely unknown due to limited exploration, though estimates suggest some areas reach up to 100 meters deep. This variability impacts the interaction between cosmic rays and methane lakes, as deeper regions are more susceptible to prolonged exposure to high-energy particles. The boundary zone thus becomes a site where geological and astronomical processes intersect, shaping both the current environment and future evolution of Titan's surface. Seasonal changes on Titan cause the shorelines of Mare to shift over time, with methane evaporating during warmer months and condensing back onto the surface as seasons change. This cycle has been ongoing for billions of years since Titan's formation alongside Saturn. The boundary zone represents both a dynamic interface and a stable feature in this ancient environment. The chemical interactions at the boundary between dry land and methane lakes on Titan hint at broader cosmic processes. These high-energy particles, originating from distant stars and supernovae, journey through space for millions of years before interacting with Titan's dense atmosphere. This process not only affects the immediate environment, but also provides clues about how complex organic compounds might form in other parts of the universe under similar conditions. The boundary zone on Titan stands as a unique laboratory for understanding these cosmic-scale transformations. The shifting boundary between dry land and Mare also influences the composition of organic compounds near the shorelines. As methane evaporates from the lake, it carries with it a mixture of complex hydrocarbons that can settle on nearby surfaces. This process leaves behind a thin layer of organic residue rich in molecules like benzene and propane. Over time, these deposits accumulate, creating a record of chemical activity that spans Titan's long history. This layering effect is akin to sedimentary rock formation on Earth, but occurs under vastly different conditions. The extreme cold ensures that the deposited materials remain stable for extended periods, preserving a detailed chronology of past environmental changes. This boundary zone thus serves as both an active site of chemical interaction and a passive archive of Titan's climatic history. Each shift in the shoreline contributes to this ongoing record, offering scientists invaluable insights into the Moon's atmospheric evolution over billions of years. The boundary where dry land meets Mare is not just a physical division, but also a dynamic interface between geological processes and cosmic influences. As methane evaporates and condenses, it carries with it traces of complex organic molecules that have been altered by cosmic rays. These interactions create a unique chemical signature at the shoreline, marking each seasonal cycle with subtle changes in composition. This process highlights how Titan's environment is constantly evolving, shaped by both internal and external forces. At this boundary, the temperature fluctuates slightly between -179 degrees Celsius on the lake's surface and even colder temperatures on the surrounding dry land. The contrast creates a thermal gradient that drives convection currents within the methane layer near the shore. These currents facilitate the mixing of different chemical compounds, leading to complex reactions that are not fully understood. This boundary zone becomes a microcosm of Titan's larger environmental dynamics, where small-scale processes contribute to the Moon's broader geological and atmospheric systems. The interaction between cosmic rays and organic molecules at Mare's edge is particularly intriguing. These high-energy particles can Cosmic rays penetrate up to 3 meters into Titan's methane lakes, where they interact with molecules in a process that unfolds over geological epochs far longer than any civilization has persisted on Earth. These high-energy particles break down larger hydrocarbons and release hydrogen atoms that form new compounds like acetylene and ethylene. This cycle of decomposition and reformation is crucial for maintaining the chemical balance within Mare, Titan's largest lake. The depth of some areas in Mare reaches about 100 meters, providing ample space for these reactions to occur. Near the equator, cosmic ray diffusion rates are 10 times higher than at the poles due to variations in magnetic field strength and atmospheric density. This uneven distribution creates distinct chemical environments within the lake, with more complex molecules forming closer to the equator where the rays penetrate deeper. These differences highlight how Titan's environment is not uniform, but rather a patchwork of diverse conditions that influence its chemistry. The temperature at the surface of Mare averages around minus 179 degrees Celsius, cold enough for methane to remain liquid instead of vapor or ice. This frigid condition allows complex organic molecules to form and persist in a way they cannot on Earth. The coldest place in our solar system where liquids exist is not deep space, but on this distant moon orbiting Saturn. Here, the chemical reactions are slow and deliberate, taking centuries to millennia for significant changes. The methane lakes play a pivotal role in Titan's carbon cycle by recycling organic molecules over billions of years. These cycles contribute to the formation of complex hydrocarbons that could potentially serve as building blocks for life. The process is not just about breaking down larger compounds, but also about creating new ones, such as acetylene and ethylene, which are essential components in more intricate molecular structures. Mare's vastness, spanning an area larger than any of Earth's Great Lakes, enables these chemical processes to occur on a scale that is both grand and slow. The lake covers approximately 400,000 square kilometers, providing a significant reservoir for cosmic ray interactions. This immense space allows for the gradual accumulation and transformation of organic molecules over geological timescales. The depth of Mare remains largely unknown in many areas, but it is estimated to be up to 100 meters deep in some regions. These depths offer an environment where complex chemical reactions can occur without being disturbed by surface conditions. The process of cosmic ray diffusion and the subsequent formation of organic compounds underscores how Titan's lakes serve as a laboratory for understanding the origins of life's building blocks under extreme cold conditions. The methane lakes on Titan are not just repositories of complex hydrocarbons. They also act as catalysts in a slow, deliberate dance of chemical transformation. These transformations occur over geological timescales that dwarf human lifespans, with reactions taking centuries or even millennia to reach completion. The iron in your blood was forged in stars that died before our sun existed. And similarly, the organic molecules forming within Mare have been shaped by cosmic events far beyond Titan's immediate environment. Waves on Mare, another of Titan's lakes, were detected in 2014, with heights reaching about 2 centimeters. These waves are a direct result of wind speeds averaging around 1 meter per second, creating ripples that propagate across the surface of these alien seas. This gentle stirring mixes the chemical soup beneath, ensuring that newly formed compounds can be distributed throughout the lake's depths and further participate in ongoing reactions. The recycling process within Kraken Mare involves not only the formation of new molecules, but also their eventual decay back into simpler forms. This cycle ensures a constant turnover of organic material, maintaining a delicate balance between synthesis and degradation. The coldest place in our solar system where liquids exist is not deep space, but on this distant moon orbiting Saturn, where these processes unfold with precision over unfathomable periods. The depth of some areas within Kraken Mare reaches about 100 meters, providing ample space for complex chemical reactions to occur. These reactions are influenced by the varying intensity of cosmic rays that penetrate different parts of the lake. Near the equator, where magnetic field strength is lower and atmospheric density thinner, cosmic rays can diffuse up to 3 meters below the surface, creating conditions ripe for the formation of more intricate molecules. This uneven distribution highlights how Titan's environment is not uniform, but rather a patchwork of diverse chemical microcosms. Each molecule within Kraken Mare has its own journey through time and space. Some are formed in the upper layers where the interaction between cosmic rays and methane molecules within Kraken Mare is a process that occurs over vast timescales, extending back to Titan's formation billions of years ago. These high-energy particles travel through space for millions of years before encountering the Moon's dense atmosphere, where they penetrate up to 3 meters into the liquid hydrocarbons below the surface. At this depth, cosmic rays break down larger hydrocarbon molecules, releasing hydrogen atoms that form new compounds like acetylene and ethylene. This microscopic dance of particles contrasts sharply with the massive gravitational influence of Saturn, which dominates Titan's orbit. The Moon is held in a delicate balance by its parent planet's immense pull, yet at the same time, individual methane molecules are rearranged by cosmic rays in a process that unfolds over geological epochs. The surface temperature of Kraken Mare averages minus 179 degrees Celsius, cold enough for methane to remain liquid rather than vapor or ice. This frigid environment contrasts with the extreme heat found closer to Saturn, where temperatures can reach thousands of degrees Celsius due to tidal forces. The chemical reactions within Titan's lakes are influenced by these variations in temperature and pressure across the Moon's surface. Despite the cold, Kraken Mare is not a static body of liquid. It has evolved over billions of years, shaped by processes that defy human timescales. The depth of some areas within Kraken Mare reaches up to 100 meters, though much remains unknown about its average depth due to limited exploration. This vastness in scale, from the microscopic interactions of methane molecules to the expansive depths of the lake, highlights the complexity of Titan's environment. The atmosphere on Titan is composed primarily of nitrogen and methane, with traces of other hydrocarbons like ethane and propane. These gases create conditions that allow for the existence of liquid hydrocarbons on its frigid surface. The density variations within this atmosphere influence the rate at which cosmic rays diffuse through Kraken-Mare's waters, creating a gradient in chemical activity across different regions. While sound cannot travel through Titan's vacuum-like environment, the chemical processes within Kraken-Mare are anything but silent. They represent a symphony of molecular interactions that have been unfolding over geological epochs far longer than any civilization has persisted on Earth. The depth and age of these lakes offer insights into the Moon's history, revealing how cosmic rays have shaped its surface chemistry over time. At the molecular level, methane behaves differently on Titan compared to Earth. The cold temperatures cause methane molecules to move slower than they do on our warmer planet, leading to unique chemical reactions that are not possible under terrestrial conditions. These reactions include the formation of complex organic compounds, some of which may have been precursors to life elsewhere in the universe. The paradox lies in how such intricate processes can occur in an environment so inhospitable to life as we know it. The depth of Kraken-Mare reaches up to 100 meters in certain areas, though its average depth remains largely unknown due to limited exploration. This vastness is a testament to the Moon's ancient history, with these lakes having existed for billions of years since Titan formed alongside Saturn. The contrast between this microscopic scale of molecular interactions and the macroscopic scale of the lake's depth underscores the complexity of Titan's environment. While we can measure the depth using sonar technology, understanding the full extent of what occurs beneath the surface requires further study. As cosmic rays penetrate Kraken-Mare's liquid hydrocarbons, they initiate a series of chemical reactions that break down larger molecules and form new ones. This process is akin to baking. Ingredients are mixed under specific conditions to create something entirely different from their original forms. In this case, the oven is Titan's frigid atmosphere, where cosmic rays act as the catalysts for these transformations. The rate of diffusion varies by a factor of 10 across different regions due to variations in magnetic field strength and atmospheric density. The temperature at the surface of Kraken-Mare averages -179 degrees Celsius, cold enough for methane to remain liquid rather than vapor or ice. This frigid environment is colder than any place on Earth, yet it supports a unique ecosystem of chemicals that interact under these extreme conditions. The contrast between this cold and the intense heat near Saturn highlights the vast range of temperatures found within our solar system. The depth of some areas. Cosmic rays, originating from distant stars and supernovae, traverse the void of space for millions of years before encountering Titan's dense atmosphere. These high-energy particles interact with methane molecules in Kraken-Mare, diffusing up to 3 meters beneath its surface. This process not only alters the chemical composition, but also contributes to a complex interplay of processes that extend beyond the immediate vicinity of these vast bodies of liquid. Understanding this interaction is crucial for unraveling Titan's history and the potential for similar processes on other celestial bodies in our solar system. The isotopic ratios within Kraken-Mare, particularly those of deuterium to hydrogen, reveal much about its ancient origins. Scientists analyze these specific measurements to understand how these lakes came into being. The higher concentration of deuterium compared to hydrogen suggests that the Moon's atmosphere may have been more hydrogen-rich billions of years ago, facilitating the formation of methane lakes through chemical reactions driven by cosmic rays. Before the methane seas formed on Titan, the Moon experienced a period marked by intense bombardment from space debris. This era, known as the Late Heavy Bombardment, occurred approximately 4 billion years ago and left its mark on the surface in the form of craters and altered landscapes. The impactors brought with them volatile compounds that contributed to the early atmosphere's composition, setting the stage for methane lakes to emerge. These impacts also influenced the distribution of cosmic rays, altering their interaction with Titan's nascent environment. The temperature at Kraken-Mare averages around -179 degrees Celsius, cold enough for methane to remain liquid rather than vapor or ice. This frigid state allows complex chemical reactions to occur within the lake's depths, driven by cosmic ray diffusion. At these temperatures, larger molecules can form without breaking down due to thermal energy, leading to a unique chemistry that is not found on Earth. Surprisingly, despite this extreme cold, certain organic compounds can undergo unexpected transformations, potentially offering clues about prebiotic chemistry in an extraterrestrial setting. Kraken-Mare's depth remains largely unknown, with estimates suggesting it could be as deep as 100 meters in some areas. However, the exact average depth is still a mystery due to the challenges of exploring such remote and hostile environments. The varying depths across Kraken-Mare influence how cosmic rays interact with its liquid methane. In shallower regions, where the lake is only a few meters deep, the interaction zone may be entirely within the liquid, while in deeper areas, it extends further below the surface. The chemical reactions initiated by cosmic ray diffusion on Titan have been ongoing for billions of years, shaping the Moon's landscape and atmosphere. These processes are part of a larger cycle that connects the Moon to its parent planet, Saturn, through shared materials and energy sources. The isotopic ratios found in Kraken-Mare suggest that some of the hydrogen atoms present were likely delivered by comets or asteroids during Titan's formation, highlighting the interconnectedness of our solar system's history. This ancient process continues today, with cosmic rays constantly reshaping the chemical composition of Titan's methane lakes. Cosmic rays, high-energy particles from distant stars and supernovae, penetrate up to 3 meters into Titan's methane lakes, altering their isotopic composition. These rays interact with methane molecules at varying depths, creating a chemical signature that reflects Titan's long history. The process is not uniform. Cosmic ray diffusion rates vary by a factor of 10 across different regions due to differences in magnetic field strength and atmospheric density. This variability means some areas experience more intense radiation than others, leading to localized enrichments or depletions of specific isotopes. The pressure within these methane lakes is significantly higher than on the surface, reaching approximately 10 atmospheres at a depth of 3 meters. This increased pressure affects the chemical reactions occurring beneath the lake's surface, influencing how cosmic rays interact with methane molecules. On Earth, such pressures would be found in deep-sea environments, but here they exist in an environment where liquid methane is stable due to extreme cold. The temperature within these depths remains consistently around -179 degrees Celsius, a condition that allows for unique chemical processes not possible on our warmer planet. In some parts of Mare, the largest lake on Titan, cosmic rays can break down larger hydrocarbons into smaller molecules, releasing hydrogen atoms in the process. These reactions contribute to the formation of new compounds like acetylene and ethylene, enriching the chemical diversity of the lakes. This transformation is a slow but continuous process that has been unfolding since Titan's formation billions of years ago. It's remarkable how these high-energy particles, traveling through space for millions of years, can influence such minute details on this distant moon. The isotopic variations caused by cosmic ray diffusion offer clues about the age and origin of Titan's methane lakes. These chemical signatures are like fingerprints left behind by ancient stellar events that occurred long before our sun was born. The iron in your blood, for instance, was forged in a star that died billions of years ago, much like the isotopes now present in Titan's lakes. This connection between cosmic phenomena and terrestrial biology underscores the interconnectedness of all matter in the universe. At certain depths within Mare, the concentration of heavier isotopes increases due to the selective diffusion caused by cosmic rays. This phenomenon creates a vertical gradient where lighter molecules are more readily displaced than their heavier counterparts. The process is akin to how water filters through sand, but on a molecular scale and under extreme conditions. Understanding these gradients helps scientists piece together the history of Titan's atmosphere and surface interactions over time. Cosmic ray diffusion not only affects methane composition, but also influences the physical properties of the lakes themselves. The increased density at deeper levels can lead to stratification, where layers of liquid with different isotopic compositions form distinct strata within the lake. This layering is a result of complex interplay between cosmic radiation and Titan's unique environmental conditions. It provides insight into how these ancient seas have evolved over geological epochs, shaping Titan's surface in ways that are still being discovered by our distant probes. The pressure on a human body submerged in liquid methane at Titan's surface is equivalent to being underwater, but with a denser fluid than water. Methane here has a density of about 0.42 grams per cubic centimeter, making it more buoyant than Earth's seawater. The cold temperature, hovering around -179 degrees Celsius, ensures methane remains liquid rather than freezing into ice or evaporating into gas. This unique environment contrasts with the familiar sensation of floating in water on Earth. Shift Imagine if you could float effortlessly, yet feel a constant pressure from a fluid denser than any found naturally on our planet. The buoyancy would be so pronounced that even heavy objects might seem to float easily, much like how oil floats on water due to density differences. This phenomenon highlights the stark difference between Earth's environments and those of distant moons. Return. In this scenario, your body, composed largely of water, would experience a peculiar sensation of weightlessness, combined with the persistent pressure from the denser methane. The liquid's viscosity is also lower than that of water, which means it offers less resistance to movement, but still provides a noticeable push against your skin and limbs. Cosmic rays penetrate up to 3 meters into Titan's methane lakes, interacting with molecules in ways that alter their chemical composition. These high-energy particles travel through space for millions of years before reaching Titan's atmosphere. The interaction between cosmic rays and hydrocarbons creates a unique process where larger molecules are broken down into smaller ones, releasing hydrogen atoms that form new compounds like acetylene and ethylene. Shift. This process is akin to the slow cooking of complex organic molecules in a vast chemical laboratory. Over billions of years, these reactions have built up a rich tapestry of hydrocarbons beneath Titan's surface. Yet, paradoxically, this deep space environment offers conditions that are far more stable for preserving molecular complexity than many environments on Earth. Return. The depth at which cosmic rays can penetrate the methane lakes is significant, as it means they affect not just the surface, but also deeper layers where complex chemistry occurs uninterrupted by external factors like weather or tides. This stability allows for a continuous and consistent interaction that shapes Titan's chemical landscape over geological timescales. The pressure you would feel while submerged in Calmness is equivalent to being underwater on Earth at depths of about 40 meters, but with the added density of methane. This pressure increases linearly with depth, meaning deeper parts of the lake exert even more force against your body. However, due to the lower gravity on Titan compared to Earth, you would still feel lighter overall. Shift. Consider that while the gravitational pull is weaker, the increased density of the liquid counteracts this effect, creating a unique balance between buoyancy and pressure. This balance is reminiscent of how divers experience different pressures at varying depths in Earth's oceans, but with a twist due to Titan's lower gravity. Return. As you descend deeper into Calmness, the temperature remains constant at minus 179 degrees Celsius throughout the liquid column, unlike on Earth where water temperatures can vary significantly with depth. This uniformity provides a consistent environment for chemical reactions and biological processes, should any exist in this alien sea. Notably, the cold conditions on Titan prevent complex molecules from breaking down too quickly, preserving them over long periods. The interaction between cosmic rays and methane molecules creates a unique chemical signature within Calmness that reflects Titan's long history. These high-energy particles break down larger hydrocarbons into smaller ones, releasing hydrogen atoms that form new compounds like acetylene and ethylene. This process has been ongoing for billions of years. Shift. Cosmic rays not only affect the surface, but also influence deeper layers by breaking apart molecules at depths up to 3 meters below the lake's surface. This deep penetration ensures a continuous chemical transformation, fostering an environment where complex organic compounds can form and persist over geological timescales without interruption from external factors like weather or tides. The depth at which cosmic rays can penetrate the methane lakes is significant, as it means they affect not just the surface, but also deeper layers where complex chemistry occurs uninterrupted by external factors like weather or tides. This stability allows for a continuous and consistent interaction that shapes Titan's chemical landscape over geological timescales. Kraken-Mare's depth varies across its vast expanse, with some areas reaching depths of up to 100 meters. The pressure at such depths would be equivalent to being underwater on Earth at around 40 meters deep, but the lower gravity on Titan means you'd still feel lighter overall. This unique balance between buoyancy and pressure is a result of both the liquid's density and Titan's gravitational field. The chemical composition of Kraken-Mare is a direct result of cosmic ray diffusion and local atmospheric conditions. Specifically, cosmic rays with an energy level of at least 10 GeV break down methane molecules into smaller hydrocarbons like ethylene and acetylene. This process has been ongoing for billions of years, shaping the lake's chemistry in ways that are unique to Titan's environment. The presence of complex organic compounds within these lakes could provide clues about the potential for life elsewhere in the universe, though any such organisms would have. Cosmic rays not only affect the chemistry of Kraken-Mare, but also influence its surface dynamics. The interaction between these high-energy particles and methane molecules can cause small-scale disturbances at the lake's surface, contributing to wave formation. In 2014, the Cassini spacecraft detected waves on Lakebeds measuring about 2 centimeters high, indicating wind speeds of around 1 meter per second. The chemical composition of Kraken-Mare is a direct result of cosmic ray diffusion and local atmospheric conditions. Specifically, cosmic rays with an energy level of at least 10 GeV break down methane. Saturn's magnetic field interacts with Titan in complex ways, shaping both its atmosphere and surface chemistry. Near the equator, where the magnetic field is strongest, cosmic ray diffusion rates are 10 times higher than at the poles. This variation creates a chemical gradient within Kraken-Mare, leading to different concentrations of compounds across the lake. These variations have profound implications for organic molecule formation in Titan's lakes. The increased energy from higher cosmic ray diffusion near the equator accelerates the breakdown of larger hydrocarbons into smaller ones. These processes are akin to a molecular dance, where each step is choreographed by high-energy particles that travel millions of years before interacting with methane molecules. The magnetic field also influences Titan's weather systems. Winds on Titan, driven by temperature differences and cosmic ray interactions, create subtle waves in Lakebeds. Measuring about 2 centimeters high, these waves are a result of wind speeds averaging around 1 meter per second. This phenomenon highlights how even in this cold environment, energy is constantly at play. The depth of Mare remains largely unknown, but estimates suggest it reaches up to 100 meters in some areas. Cosmic rays penetrate up to 3 meters into the lake's depth, affecting its chemical composition. These high-energy particles break down larger hydrocarbons and release hydrogen atoms that form new compounds like acetylene and ethylene. This process is a testament to the enduring influence of cosmic forces on Titan's surface. Despite the frigid temperatures at -179 degrees Celsius, organic molecules can still form complex structures in Titan's lakes. However, these structures are limited by the available energy. Larger molecules would require more energy than is present in this cold climate. This limitation underscores the delicate balance between cosmic forces and environmental conditions on Titan. The magnetic field generated by Saturn's interaction with Titan not only shapes the Moon's surface, but also influences its global weather patterns. The varying strengths of the magnetic field across Titan's surface lead to different diffusion rates for cosmic rays, affecting atmospheric particle distribution. This interplay highlights how distant celestial bodies can have a profound impact on each other over vast distances and timescales. The varying magnetic field strengths across Titan's surface create unique conditions for cosmic ray diffusion, leading to different chemical compositions in various parts of its lakes. In some regions, where the magnetic field is stronger, cosmic rays penetrate deeper into the liquid, altering more molecules and creating a richer mix of hydrocarbons. This complexity mirrors the intricate processes at work within Earth's own atmosphere, where similar interactions between particles and fields shape weather patterns. Saturn's magnetic field extends far beyond its surface, enveloping Titan in an invisible cocoon that subtly influences the Moon's environment. The field lines stretch outwards, guiding cosmic rays towards specific areas on Titan's surface. This phenomenon is akin to how Earth's magnetosphere protects our planet from solar winds and cosmic radiation. On Titan, this magnetic influence not only affects the chemical composition of its lakes, but also plays a role in shaping its atmospheric dynamics. This interplay between Saturn's magnetic field and Titan's environment underscores the interconnectedness of celestial bodies within our solar system. The forces at work here are ancient, dating back to the formation of these planets billions of years ago. Yet, they continue to shape not just the physical landscape, but also the chemical processes on Titan's surface, processes that might one day provide clues about the origins of life itself. Cosmic rays bombard Titan's atmosphere, interacting with methane and nitrogen molecules to form complex organic compounds deep within Mare. These high-energy particles can penetrate up to 3 meters into the lake's liquid surface, breaking down larger hydrocarbons into smaller ones and releasing hydrogen atoms that contribute to the formation of new compounds like acetylene and ethylene. Mare's depth reaches up to 100 meters in some areas, with an average depth remaining largely unknown due to the Moon's remote location and challenging exploration conditions. The lake's bottom remains shrouded in mystery, but it likely harbors even more complex interactions between cosmic rays and organic compounds than those seen near the surface. The varying magnetic field strength and atmospheric density across Titan create a patchwork of chemical diversity on its surface. In some regions, cosmic ray diffusion rates are 10 times higher than others, leading to significant differences in the composition of methane lakes at different locations. This uneven distribution highlights how environmental factors can shape planetary chemistry over vast distances. Meteorite impacts on Titan's surface introduce another layer of complexity to Kraken-Mare's chemical makeup. When a meteorite strikes the moon, it not only displaces material, but also triggers localized heating events that alter the surrounding environment. These impact sites may release trapped gases and increase the rate of cosmic ray diffusion in nearby areas, permanently altering the lake chemistry. The process by which cosmic rays influence Kraken-Mare is both ancient and ongoing. The high-energy particles have been interacting with Titan's atmosphere since its formation billions of years ago. This interaction has played a crucial role in shaping the moon's surface and atmospheric composition over geological timescales far beyond human comprehension. Each impact event adds another layer to this long-standing process, contributing to the unique chemical signature of Kraken-Mare. Understanding the influence of cosmic ray diffusion on Titan's climate dynamics requires consideration of global weather patterns. These high-energy particles contribute not only to local changes, but also affect broader atmospheric circulation and methane evaporation rates across the moon's surface. This interconnected system demonstrates how small-scale processes can have far-reaching effects, influencing the entire environment of this distant world. The depth at which cosmic rays penetrate Kraken-Mare varies significantly depending on local atmospheric conditions and magnetic field strengths. Near the equator, where Titan's magnetic field is strongest, these particles can diffuse up to 3 meters into the lake's liquid hydrocarbons. In contrast, near the poles, this penetration depth decreases due to weaker field interactions. This uneven diffusion pattern creates a complex chemical gradient within Kraken-Mare, with different regions experiencing varying levels of molecular breakdown and recombination. The result is a dynamic interplay between cosmic ray diffusion and local weather patterns that shapes the chemistry of the lake over time. The interaction between cosmic rays and methane molecules in Kraken-Mare leads to the formation of new compounds such as acetylene and ethylene, which are integral components of Titan's complex organic chemistry. These reactions occur at a rate that is slow by Earth standards, but significant on geological timescales. The process is akin to a slow-burning fuse, where each cosmic ray interaction contributes incrementally to the chemical evolution of the lake. This gradual transformation underscores the deep time perspective required to understand processes on Titan, where changes unfold over epochs far beyond human lifespans. Meteorite impacts introduce an additional layer of complexity into this chemical dance. When a meteorite strikes Kraken-Mare, it not only stirs up the liquid, but also introduces new elements and compounds that alter the lake's chemistry permanently. The shockwave from such an impact can disturb methane layers deep beneath the surface, mixing inorganic materials with organic compounds. This interaction creates unique chemical signatures within specific regions of the lake, marking the site of past collisions for potentially billions of years to come. These disturbances highlight how external forces play a crucial role in shaping Titan's chemical environment. The temperature at Kraken Mare remains consistently cold, averaging around -179 degrees Celsius, which is colder than any natural surface on Earth. This extreme cold ensures that methane and ethane remain liquid rather than freezing into ice or evaporating into gas. A meteorite strikes one of Titan's methane lakes, sending shockwaves through the liquid that would be inaudible to human ears due to the lack of sound propagation in this environment. The impact creates ripples on the surface, but the real transformation happens beneath. Cosmic rays penetrate up to 3 meters deep, altering the chemical composition of the methane and ethane mixture. This moment is a snapshot in time that encapsulates billions of years of geological activity. Each impact contributes to Titan's unique chemistry, where organic compounds are formed through cosmic ray interactions. These processes, though silent, have been shaping the Moon's surface for eons, far longer than any human civilization has existed. The energy from the meteorite dissipates over time, leaving behind a lake that is richer in complex molecules. The depth of Kraken Mare, Titan's largest lake, remains largely unknown despite extensive studies. Scientists estimate it to be around 100 meters deep in some areas, but variations in terrain and sediment layers make precise measurements challenging. This uncertainty adds an element of mystery to the Moon's surface features. The meteorite impact not only disturbs the surface, but also stirs up deeper layers, potentially redistributing sediments that have settled over millennia. Cosmic ray diffusion rates vary across Titan due to differences in magnetic field strength and atmospheric density. Near the equator, where the magnetic field is strongest, cosmic rays can penetrate more deeply into the lakes compared to polar regions. This uneven distribution means that some parts of Kraken Mare experience a higher rate of chemical alteration than others. The meteorite impact at this specific location could have a lasting effect on the local chemistry, altering it in ways that will take time to fully understand. The organic compounds formed through cosmic ray interactions are limited by Titan's cold climate and low energy availability. Larger molecules require more energy to form, but the frigid temperatures on Titan restrict such processes. Despite these limitations, complex hydrocarbons can still emerge from the interactions between cosmic rays and methane in Kraken Mare. The impact of a meteorite introduces new elements into this delicate balance, potentially creating transient chemical conditions that could last for centuries or longer. The moment when a meteorite impacts one of Titan's lakes is fleeting but profound. This event marks an instant where the Moon's ancient chemistry is altered forever. While such impacts are rare on Titan, they serve as reminders of the dynamic forces at play in this distant world. The ripples caused by the impact will eventually subside, leaving behind a lake that carries within it the story of its encounter with cosmic debris. This singular event contributes to the ever-evolving narrative of Titan's surface and atmosphere. Energy from the impact heats the methane lake locally, creating a temporary steam-like vapor that rises into the cold air above. This vaporization process is unusual on Titan, where liquid methane rarely encounters temperatures high enough to evaporate. The meteorite's collision introduces not only new elements, but also kinetic energy that disrupts the normally calm surface of Kraken Mare. For a brief period, the lake experiences turbulence unseen for millennia, as waves spread out from the impact site at speeds influenced by Titan's low gravity and dense atmosphere. These ripples are faint compared to earthly oceanic disturbances, yet they represent significant change in this frozen world. Cosmic ray diffusion plays a significant role not only in altering the chemical composition of Titan's lakes, but also in shaping their future. These high-energy particles penetrate deep into Kraken Mare, breaking down larger hydrocarbons into smaller molecules and releasing hydrogen atoms that can form new compounds like acetylene and ethylene. This process contributes to the formation of complex organic molecules, which could potentially serve as building blocks for life under different conditions. Over billions of years, these interactions will gradually change the chemical landscape of Titan's methane seas. The depth of Kraken Mare remains largely unknown, with estimates suggesting some areas may reach up to 100 meters. However, cosmic rays can penetrate up to 3 meters beneath the surface, where they initiate a cascade of molecular transformations. This process is akin to an invisible chef stirring the pot, slowly cooking up new compounds in this alien kitchen. The rate at which these reactions occur varies across Titan due to differences in magnetic field strength and atmospheric density, creating a patchwork of chemical activity on its surface. As Saturn continues to evolve over billions of years, it will influence Titan's environment through gravitational forces and radiation. These subtle changes could lead to shifts in the Moon's orbit or even affect its internal heat generation. In turn, this might alter the dynamics of methane lakes like Kraken Mare, potentially leading to more frequent mixing between different layers of liquid. This interplay highlights how a distant planet can indirectly shape the chemical evolution on one of its moons over unimaginable timescales. The complex organic molecules formed by cosmic ray diffusion in Titan's methane seas are not merely curiosities. They hint at potential pathways for life elsewhere in the universe. On Earth, similar processes occur within deep-sea hydrothermal vents, where unique ecosystems thrive without sunlight. These environments demonstrate that life can exist under conditions far removed from what we typically associate with habitability. The organic compounds on Titan could be precursors to more complex structures, though they remain limited by the cold temperatures and lack of larger energy sources. As Saturn continues its slow evolution, its gravitational pull subtly affects Titan's orbit and rotation. This gradual change might result in shifts within Kraken Mare over billions of years, including variations in depth and composition due to altered mixing patterns caused by changing tidal forces. The lakes on Titan are not static. They evolve alongside their parent planet, a reminder that even the most stable-seeming environments are subject to cosmic influences beyond immediate perception. In the deep future, as Titan's methane seas continue to be shaped by cosmic rays and Saturn's evolving gravitational field, these lakes will undergo transformations far more dramatic than anything we can currently observe. The organic compounds formed within them may eventually reach a point where they could support rudimentary forms of life, given the right conditions, though such possibilities remain speculative at this time. Meanwhile, on Earth, scientists continue to study these distant bodies, seeking clues about our own planet's past and future in the chemical processes unfolding billions of miles away. Cosmic rays penetrate Kraken-Mare's methane lakes, initiating chemical reactions that defy expectations. These high-energy particles travel through space for millions of years before interacting with methane molecules in Titan's dense atmosphere. They can reach depths of up to 3 meters beneath the lake's surface, where temperatures hover around -179 degrees Celsius. This process creates complex organic molecules, hinting at prebiotic conditions. On Earth, similar reactions occur within clouds, but cosmic rays here are a primary driver, shaping Titan's chemistry in isolation from solar influence. Within Kraken-Mare, the largest lake on Titan, these interactions break down larger hydrocarbons into smaller ones, releasing hydrogen atoms that form new compounds like acetylene and ethylene. This transformation takes place over geological timescales, far beyond human lifespans. The complexity of these molecules is surprising given the extreme cold, which typically limits molecular interactions. Yet, in this frigid environment, cosmic rays provide the energy needed to sustain chemical reactions. At -179 degrees Celsius, methane remains liquid on Titan's surface, a condition unique in our solar system. These lakes are not just repositories of simple hydrocarbons, but dynamic environments where organic molecules can form and evolve. The depth of Kraken-Mare is estimated at around 100 meters in some areas, with an average depth that remains largely unknown. This uncertainty adds to the mystery of how far cosmic rays penetrate beneath the surface, potentially influencing deeper layers of complex chemistry. Imagine standing on the shore of Kraken-Mare, where methane rivers carve intricate channels and lakes stretch endlessly under a dim orange sky. The wind moves at a gentle pace, barely stirring the liquid surface. Waves detected by Cassini in 2014 are just 2 centimeters high, indicating wind speeds of around 1 meter per second. This serene environment belies the intense cosmic activity occurring beneath the waves, cosmic rays that travel millions of years to reach Titan and initiate chemical reactions within its lakes. These cosmic rays, originating from distant stars and supernovae, interact with methane molecules in Kraken-Mare, breaking them down into smaller components. Hydrogen atoms are released, which then form new compounds like acetylene and ethylene. This process is akin to a slow, deliberate dance where each step taken by these high-energy particles leads to the creation of complex organic molecules. On Earth, similar processes occur in deep-sea hydrothermal vents, where life may have first emerged. Yet here on Titan, they unfold under conditions vastly different from our home planet. At Kraken-Mare's surface, the temperature hovers around -179 degrees Celsius, cold enough for methane to remain liquid. Below this icy crust, cosmic rays can penetrate up to 3 meters into the lake's depth, affecting chemical reactions that occur at these frigid temperatures. This depth is significant because it means that even on a moon as distant and isolated as Titan, the universe's high-energy particles have an intimate influence on its surface chemistry. The process of molecular breakdown and recombination happens over geological timescales, far longer than any human lifetime can comprehend. These cosmic rays are not just random visitors. They carry with them the history of distant supernovae and ancient star systems. Each particle that collides with a methane molecule in Kraken-Mare is a messenger from beyond our solar system, carrying information about the cosmos past. The energy they bring to Titan's lakes can be compared to the power generated by millions of nuclear reactors on Earth. Yet, despite this immense cosmic force, the reactions initiated are subtle and slow, unfolding over epochs that challenge human comprehension. As these rays diffuse through the methane, they initiate a cascade of chemical transformations. Hydrocarbons break down into smaller molecules, releasing hydrogen atoms that form new compounds like acetylene and ethylene. This process is akin to a microscopic factory operating in deep freeze conditions, where every reaction must be carefully balanced against the cold. On Earth, such reactions would occur more rapidly due to higher temperatures and pressures, but here on Titan, they proceed at a glacial pace, shaped by the moon's frigid environment. The depth of Kraken-Mare remains largely unknown, with estimates suggesting some areas reach depth of around 100 meters. At these depths, cosmic rays continue their work, breaking down larger hydrocarbons into smaller ones. This process is not uniform. It varies across different parts of Titan due to the moon's varying magnetic field strength and atmospheric density. In regions where the magnetic field is weaker, cosmic ray diffusion rates are lower, leading to less chemical activity beneath the surface. Yet, this variability adds complexity to the organic chemistry unfolding in these alien seas. Imagine standing at the edge of Kraken-Mare, the largest lake on Titan. The temperature here hovers around -179 degrees Celsius, cold enough for methane to remain liquid rather than vapor or ice. As cosmic rays penetrate up to 3 meters into the lake's surface, they initiate and sustain chemical reactions that create complex organic molecules. These reactions are akin to those found in Earth's primordial soup, where simple compounds combine to form more intricate structures necessary for life. Yet on Titan, these processes occur under conditions far removed from our planet's warm seas, conditions so cold that even the most basic biological functions would be impossible. The chemical complexity emerging here hints at prebiotic conditions. Despite the extreme cold, some molecules can remain stable and react slowly over time, suggesting a potential for complex chemistry to develop in ways not previously anticipated on such an inhospitable world. The ground beneath your boots is solid methane ice, a texture unlike anything found on Earth. Each step compresses the icy surface slightly, leaving an indentation that will slowly fill with liquid methane as it warms in the distant light of Saturn. This soil is not just cold, but extraordinarily dry, lacking any familiar moisture. The pressure you exert leaves a mark that would take hours to disappear, given the sluggish pace of molecular movement at minus 179 degrees Celsius. Imagine walking on a substance that feels like frozen motor oil, viscous and resistant to your weight. Yet, this ice is far from static. It's in constant flux between solid and liquid states, a delicate balance maintained by Titan's frigid temperatures. This fluidity contrasts sharply with Earth's more rigid landscapes, where rock and soil are the dominant materials. Here on Titan, you would leave footprints that slowly melt into the surface before refreezing, a process that mirrors the Moon's slow, methodical evolution. The ground beneath your feet is not just ice, but a complex mixture of organic compounds churned by cosmic rays. These high-energy particles, traveling millions of years across the cosmos, interact with methane and ethane molecules to create intricate chemical pathways. The surface feels solid yet alive, constantly shifting as new compounds are formed deep within. This process, occurring over geological epochs, is akin to watching a glacier move, slowly but surely transforming the landscape. Without familiar landmarks or sounds, your sense of direction becomes unreliable. The horizon stretches endlessly in every direction, offering no reference points for navigation. Your footsteps leave impressions in the methane-soaked ground, each step sinking slightly into the soft earth. This sensation is both grounding and disorienting, a reminder that you are far from home, yet connected to processes older than human civilization. Imagine walking on Earth's coldest deserts, where temperatures can dip below minus 70 degrees Celsius in Antarctica. Here on Titan, it's nearly twice as cold at the surface of its methane lakes. Yet, despite this extreme chill, your body would remain protected by a thick layer of insulation, your spacesuit, and the insulating properties of the liquid methane surrounding you. The sensation is one of isolation. There are no familiar sounds to orient you, only the vastness stretching out in every direction. The ground beneath your feet is solid yet alien, composed of organic compounds that have been sculpted by cosmic rays over billions of years. These particles penetrate up to 3 meters into Titan's lakes, breaking down larger hydrocarbons and creating new molecules. The surface you walk on is a record of these interactions, each grain of sediment holding the history of countless cosmic collisions. In contrast, Earth's landscapes are shaped by water erosion, wind, and plate tectonics, processes that occur over mere geological epochs rather than eons. Here, every step feels like walking through time itself. The ground beneath your feet is solid yet alien, composed not of rock, but of organic compounds formed from cosmic ray interactions with methane. The temperature hovers at minus 179 degrees Celsius, cold enough to freeze nitrogen into a gas on Earth. Yet this frigid environment allows complex molecules to form in ways unattainable under warmer conditions. If you were to pick up a handful of soil here, it would feel dry and brittle, unlike the moist earth back home. This terrain is not just barren, it's a testament to the unique chemical processes that have been unfolding for billions of years on Titan. The cold has slowed down molecular motion so much that reactions take place at a glacial pace compared to Earth's dynamic surface. The ground beneath your feet, composed primarily of hydrocarbons and water ice, is eerily silent. Sound waves need molecules to travel through, but the thin atmosphere and lack of dense air on Titan make it impossible for you to hear anything. Even if you shouted at the top of your lungs, no sound would carry across this vast landscape. In contrast, Earth's oceans are filled with a symphony of sounds: whales singing, waves crashing, fish swimming. Here all is still, as though time itself has slowed down. Yet beneath this silence lies an active world where cosmic rays penetrate the methane lakes up to 3 meters deep, continuously altering their chemical composition. The surface temperature hovers at -179 degrees Celsius, cold enough for methane to remain liquid rather than vapor or ice. For a human standing on the solid ground surrounding Mare, this environment would feel more like walking on the surface of Pluto than Earth. The air is thin and nitrogen-rich, with no familiar landmarks to guide you. There are no trees, mountains, or even distant horizons. The landscape stretches out in an unbroken expanse of methane-soaked terrain. The lack of sound propagation means that any attempt at communication would be futile. The silence is absolute, a stark contrast to the bustling world we know. Yet, this isolation has its own form of companionship. Cosmic rays from distant stars and supernovae constantly bombard the surface, penetrating up to 3 meters into Mare's depths. These high-energy particles are invisible but ever-present, their influence shaping the chemical composition of the lake over geological timescales. At a distance of nearly 1 billion kilometers from Earth, Titan orbits Saturn, its surface enveloped in an atmosphere rich with nitrogen and methane. The largest lake on this distant moon, Mare, spans approximately 400,000 square kilometers, larger than any of Earth's Great Lakes. Yet, despite their ancient origins dating back to the formation of Saturn itself, these lakes are far from static. They are in a constant state of flux due to cosmic rays that bombard Titan's surface and penetrate up to 3 meters into its methane seas. Imagine standing at the edge of Mare, where the vastness of this lake stretches beyond your field of vision. The temperature hovers around -179 degrees Celsius, cold enough for methane to remain liquid despite the frigid conditions. Yet, beneath the surface, cosmic rays are constantly bombarding the lakes, diffusing up to 3 meters deep and altering their chemical composition in ways that seem paradoxical, ancient yet ever-changing. Imagine standing at the edge of Mare, Titan's largest lake, which spans an area larger than any of Earth's Great Lakes. The surface temperature hovers around -179 degrees Celsius, cold enough for methane to remain liquid rather than vapor or ice. This frigid environment is paradoxical. While the lakes are ancient, dating back billions of years, they are also perpetually evolving due to cosmic ray diffusion. These high-energy particles penetrate up to 3 meters into Kraken Mare's depth, constantly altering its chemical composition. Imagine standing at the edge of a vast lake on Earth, watching ripples spread after tossing a stone in. On Titan, however, the surface tension of methane lakes is so different that even the smallest disturbance creates waves. These waves, no more than 2 centimeters high, are driven by winds moving at about 1 meter per second. The paradox lies in how these gentle breezes can stir such vast and ancient bodies of liquid. Kraken Mare alone spans an area larger than any of Earth's Great Lakes. Despite the frigid temperatures on Titan, where methane lakes exist as liquids rather than ice or vapor, cosmic rays play a crucial role in shaping the chemical composition of Kraken Mare. These high-energy particles can penetrate up to 3 meters beneath the surface, breaking down complex hydrocarbons and releasing hydrogen atoms that form new compounds like acetylene and ethylene. This process occurs continuously, yet paradoxically, these lakes are both ancient and ever-changing. They have existed since Titan's formation billions of years ago. Yet cosmic ray diffusion ensures their chemical composition is in constant flux. At the surface of Kraken Mare, the largest lake on Titan, temperatures hover around -179 degrees Celsius. This frigid environment allows methane to remain liquid, not vapor or ice. Yet beneath its seemingly static surface, cosmic rays continuously alter the chemistry within these lakes, a paradoxical dance of stasis and transformation. At Kraken Mare, the largest lake on Titan, cosmic rays penetrate up to 3 meters into the liquid methane, altering its chemical composition in ways that are both subtle and profound. These high-energy particles interact with methane molecules, breaking them down into smaller hydrocarbons like ethylene and acetylene. The process is so gradual it's nearly imperceptible, yet over billions of years, these interactions have sculpted the chemistry of Kraken Mare. On Titan's surface, cosmic rays penetrate up to 3 meters beneath its methane lakes, where they interact with molecules in a delicate dance of disassembly and recombination. Each high-energy particle breaks down larger hydrocarbons into smaller ones, releasing hydrogen atoms that form new compounds like acetylene and ethylene. This process occurs over billions of years, shaping the chemical composition of Titan's ancient lakes. At Kraken Mare, cosmic rays penetrate up to 3 meters beneath the surface, where they interact with methane and ethane molecules. These high-energy particles break down larger hydrocarbons into smaller ones, releasing hydrogen atoms that form new compounds like acetylene and ethylene. This process is akin to a microscopic factory operating in near perpetuity, transforming the chemical landscape of Titan's lakes. Despite their ancient origins, these lakes are far from static. Cosmic rays, high-energy particles from distant stars, continuously bombard Titan's atmosphere and penetrate up to 3 meters into its methane lakes. These interactions break down larger hydrocarbons into smaller molecules, releasing hydrogen atoms that form new compounds like acetylene and ethylene. At -179 degrees Celsius, the liquid methane in Kraken Mare remains fluid, unlike water on Earth, which would freeze at such temperatures. This paradoxical state is due to Titan's extremely cold environment, where even ice behaves unusually. Methane cannot crystallize into a typical solid form because it lacks sufficient energy for that phase transition. At the surface of Mare, the largest lake on Saturn's moon Titan, cosmic rays continuously bombard the methane-ethane mixture. These high-energy particles can penetrate up to 3 meters beneath the liquid's surface, altering its chemical composition. The process is both ancient and ever-changing. While the lakes themselves are billions of years old, their chemistry is constantly being refreshed by cosmic ray diffusion. Imagine standing at the edge of Mare, where the vastness of this lake stretches beyond human comprehension. Titan's methane lakes glisten under the faint light of Saturn, their surfaces paradoxically evoking a serene calm despite the unpredictable weather systems swirling above. As we conclude this journey through deep space calmness, remember that some mysteries lie closer to home than expected. Thank you for joining us on this cosmic sojourn. Your presence here is deeply appreciated. Don't forget to subscribe and like if you enjoyed this video. Good night, and rest well under the watchful gaze of distant stars.